Welcome everybody to the College of Architecture and Design at Lawrence Technological University, and welcome to those of you who are joining us online on our YouTube channel. My name is Dale Allen Geyer, and I'm the chair of the Architecture Department and a professor of architecture. Here at the college, we believe that the future of design is multidisciplinary, and we host a range of design degrees that include graphic design, industrial and transportation design, game design, interiors, and architecture. We track design future trends, emerging technologies, and advancements in practice as a means of crafting educational approaches in these areas. As part of this, we have a design and technology lecture series, which allows us to engage discussions in design and offer broad perspectives on where the fields are headed. And just as a heads up, we have a full month of design and technology lectures this month. In addition to today's lecture, we have one on March 28th, Frank Melendez talking about unruly matters. And on March 30th, we have Julian Bleeker talking about design fiction. And if you're interested in attending one of these upcoming design and technology lectures, you can either use one of these flyers that are around the chairs, or you can sign up through our COAD lecture page. So I'm very excited to introduce today's speaker for our Spring 2023 Design and Technology Lecture Series. It is Damon Leverett. Damon Leverett of the AIA, NCARB, and NOMA is an architect, artist, and educator with over 30 years of experience in the architecture and design industry. A senior lecturer at the College of Architecture and the School of Information at the University of Arizona. He teaches design studio, environmental systems, and computing in the arts. Damon is a proud graduate of LTU, and he's served as a adjunct instructor for us, as well as a visiting lecturer of architectural design at the University of Illinois at Urbana-Champaign. And in 2015, Damon was awarded the Distinguished Architectural Alumni Award by LTU's COAD Alumni Association. He's currently the 2023 president of AIA Arizona and a past director at the National Architectural Accrediting Board, or NAB, as we're all familiar with, since they're coming in 2 weeks to visit us. Damon's projects as lead designer include the Yavapai County Superior Court in Camp Verde, Arizona, the Archibald Granville Bush Science Center at Rollins College in Winter Park, Florida, the North Quad Room 2435 for the University of Michigan in Ann Arbor, and the Mount Sinai Medical Office and Inpatient Edition somewhere in Brazil that I can't pronounce properly. Damon's lecture today is titled Geometry Algorithms in Architecture, Exploring the Math Behind Generative Grid Systems. At the end of his lecture, we'll have a short period, about 15 minutes, for questions and answers. So please help me in welcoming Damon Leverett.
Well, first of all, I want to thank everybody for taking time out of your really busy day. There's a lot of professionals here, as well as students. You have a lot of choices to think about things when you're in school, and thank you very much for taking your time to spend with me to talk about this very influential topic. The first thing I want to tell you is that when you meet someone like me that has a little bit of gray hair like this, you might be expecting somewhat of an old school conversation. But actually, I want you to remember there's a distinction between this, that what I'm talking about is not about bringing the past into the present. It is about bringing the past into the future. That's why I wanted to talk to the students, because it's the future that can benefit from just understanding something that happened about 80 years ago with Walter Netsch and his experience being here at LTU. So let's get started. Today I'm going to talk about 5 things in general, and they are going to be to share this mathematical proof for the grid system used by Chicago architect Walter Netsch from 1960s to the 70s, and it's going to be divided into his experience here at LTU, influences on art and design, mainly my art as well. The math behind the chrysanthemum, and I promise you don't need a calculator or taking notes. It's just a little bit of math, but I have to get into that. Also, the chrysanthemum expanded. I'll talk about what the chrysanthemum is. And then I had to add a chapter last week, actually about 4 days ago, actually on artificial intelligence, because that topic is a wild, it's like wildfire, essentially. And I actually did a little more work on that to share at the end on my thoughts on that as well. So let's get started with Walter here at LTU. Walter Netsch, 1920 to 2008, used grid systems widely in his practice with Skidmore, Owens, and Merrill, SOM, from 1947 to 1979. And Netsch explored geometric grid systems he called field theory. And in this field theory, he utilized many of these ideas in some of the buildings that he constructed. There's over 20 buildings throughout the Midwest that utilize this field theory. And this is an example here, which is the Hardin Library at the University of Iowa in 1974. But one you may be familiar with is probably his most accomplished and famous work, which is the Air Force Academy Cadet Chapel in Colorado Springs. It's actually one of my favorite buildings, but it's also probably the top 30 buildings of the 20th century. It's in that category. It's actually under renovation right now. It's a $158 million renovation, and it is expected to be completed in 2027. I met Walter Netsch in the spring of 1983, so that's actually 40 years ago right now. He was a visiting lecturer at Lawrence Technological University, and as my instructor, he shared his vision of field theory and incorporated into the classwork and projects. There's a couple people here today who are were in that class with me, one that couldn't make it, but I've totally lost touch with all the people in my class, but they recently have been connecting with me on Facebook after this was announced, and hopefully we'll get together again soon. The class was also led, I want to acknowledge someone really important, and it was also led by Paul Chu Lin, Professor Paul Chu Lin, who is still a resident of Troy, Michigan, and he was an architect for Gruner Berkowitz, actually, for many years, and a very dedicated teacher. And I just want to acknowledge the fact that he was actually the person who was always there in every class, and then Walter would come every other week. So one teacher would keep it going, and then Walter would make his presence known. And so Paul Chu Lin was really important to this. So you're getting a little bit of the feel of the chrysanthemum. There's no point in this conversation where I can't show you. I have to start showing you at some point. So Netsch began working with us by showing us how to draw this geometry by hand, because there were no computers yet when I started here in 1978, and you had to use a compass, an adjustable triangle, a parallel bar, eraser shield. That's it. I mean, you know. So it was actually really complicated to build one of these things, but just simple tools were all we had available. Now, Walter actually believed in, this is something I had never been done in any studio class here, and I had some really good professors here, I just want to say. But he said, hey, I want you to just take a marker and start thinking about fields of color, linkages, nodes, and think about density and comparison. And so he would have us take these geometries and just apply color to them. And it's actually a very difficult thing to do because you actually don't know where to put the color. So it's a little bit difficult in that sense. So let's move on a little bit to how it influenced my artwork and design over the years. And it all started, this always brings up a few chuckles, the people who know this photograph on the left here. But in after I graduated, well, before I graduated, actually it was after I graduated. After I graduated in 1983, I returned to LTU a year later, actually, to take a course with Professor Muldrum, who's also one to acknowledge. And when the School of Architecture acquired the Prime Medusa computer, and of course that is a office-sized computer, but the terminal is actually very small. Actually, if you go to the architecture building, the old one, and you see these pipes going into the side of the building, that's actually one of the first ones that actually linked the engineering building to the architecture building for data transfer. So there's 4 of them now. I think there were only 1 when I was here. So I realized that drawing the geometry by hand was very inaccurate, and that the computer gave me additional capabilities of repetition and other construction economies. I later returned to LTU in 1990 to teach the same class that Mr. Meldrum taught, called Computers in Architecture. Although I was using digital lines to construct the geometry in the computer, I was using hand-drawing methodologies to do so. So what that means is that I was using the same ideas. The people who started CAD in the 80s realized that it's a transference of hand drafting to CAD. All the generations since 1990 have only had CAD to CAD, or now it's CAD to BIM. But at one point, it was actually trying to translate your thinking about how I went from drawing by hand. But one of the things I discovered is that using that methodology actually creates all these inaccuracies. And to 3 decimal points or so, actually when you created this diagram, which Walter called a mesa. So a mesa is when you take each of these small flowers we call chrysanthemums, and you link them together, which I'll discuss how they're actually linked. And when you do that, you create a field, essentially, or what he called a mesa. It was actually the first moment when I realized that this repeating was a problem. And so I had to think about, this is the first time I actually thought about creating a formula for it, because using a data formula or an algorithm will give me much more precise results. But it was actually many, many years, actually it wasn't until 2 years ago that I actually figured that out, and I'll talk about that in a moment. But I went on to do some artwork, and this is a piece I did in 1986. I keep a lot of drawings, actually, you can see. And it is actually done in pencil. It's actually ink with colored pencil. And so it's, again, Walter's ideal of helping us to understand, to look at regions, linkages and nodes, and think about how densities and lightness can be an influence in how you think about designing space and also areas. And it continued on. This is one from 2017. It's a much bigger, I like the blow up of this. It's a much bigger image, but essentially it's now taking a different tool, which is taking Photoshop and using that to actually bring into this conversation, whereas before I was using colored pencil and markers. So, anybody use markers anymore? In recent years, I have gone on to study this more, particularly using Illustrator. So actually using Illustrator is a little bit more flexible tool to be able to study transparencies, additional connections, and exploring other ideas about how this field works. So there's been a couple practical things that I've done. In recent years, I teamed up with my wife, who's an architect, and also a Tucson master quilter by the name of Barbara Clark, to develop a quilt based on the theory of field theory. So we actually formed a team. It's called the Leverett Clark Project, and the 3 of us got together, and we had to print out the field and then transfer it into something that became a pattern that she could actually sew on. So this is actually one project where we actually did that. And this is one we're working on right now. So we continue to work on field theory in her quilting practice. And it's really, and this is what I meant by bringing the past into the future. For Barbara, she's, my parents' age, but to have her experience something from the 40s, you know, and then in the future, the present, actually doing it, which is technology-based, it's just an amazing collaboration between the three of us, and we've had an amazing time doing that. All right, let's talk about the math behind the chrysanthemum, which is really the flower that we've been referring to. The structure of the Netsch chrysanthemum focuses on the disc floret, or the heart of the flower, which expresses natural geometric order related to its biological processes and success as an organism. Just to understand the parts of the flower, the structure is observed a little bit better in a different flower, which is actually the daisy. So this is actually easier to see it. Actually, you can see it in a chrysanthemum as well, but you can see it better in a daisy because the actual components of it are a lot more visible. Where the disc floret is designed and easier to compare to the geometrical model. So let's look at what happens here. There are several attributes of both the natural and geometric systems that stand out. We had a great conversation last night. We talked about this idea as being biomimetic. Biomimetic, which means it's a natural system that we can understand and use in the architectural world and the design world. There's a couple things going on. So everybody knows this every day. You look at flowers, you see this. The reduction of the disc floret petal size as you get closer to the center. So typically in a flower like this, as you get closer to the middle, they get smaller. The next thing you might notice is they alternate in terms of their pattern, one between the other. And one of the things that we theorize that as the reason for this is that it's more efficient to collect sunlight this way. One petal doesn't create a shadow in front of the other one because they're always staggered, and as they get staggered, they get smaller. So it's much more efficient to make the organism more successful. And then finally, the most obvious thing is that the visual begins to spiral down. So it's a spiral, actually, that happens as well. So they get smaller, they zigzag, and they also spiral at the same time. So we'll see how Walter accomplished this as well. All right, so let's look at the math behind Netsch's chrysanthemum. We start with one of two main variables, the length of the side of a regular quadrilateral, which we will refer to as a quad here, which is actually member S. So you need to know how big the square needs to be to start with. And also, we also need to know the radius, which is the center of the flower to the center of the quadrilateral. And we also need to know the number of petals that you're using. So the number of petals has a big influence on how the design will have an outcome. And I'll talk about how many petals. It's actually to infinity. But you have a lot of flexibility in the number of petals you can use. So for our conversation, we start the length of the side S and we express the equation. This is actually the answer at the beginning of this conversation, but I still like to do this because sometimes people like to go back and forth. So the radius is equal to the side divided by the square root of 2 times the tangent of angle C. So let's find out what all these other angles are all about. To better understand what's going on, the initial quad, we need to see the relationship up close, which I've done here, which reveals that the length of side S is directly proportional to the radius. So as the length of the side of S gets bigger, so does the radius get bigger. So a direct proportional relationship. We define our quad by identifying its points, but most importantly, establishing point E. So point E is the middle. It's just the middle of the quadrilateral, which is the center. It is useful in doing this because I know some of the students here have actually taken coding, and this function, actually say method, called rect mode equals center is something, if you've done coding in Python, it doesn't matter what language you're using, Python, processing, C, this rect mode function is something you do when you want to be in the middle of an object as opposed to being in a corner of an object. So another one is rect mode corner, and there's some other ones as well. This actually begins the process of thinking about what language I'm using, which is called processing, or P5.js, which is processing for JavaScript. So we need to find out what F is in order for this to all happen. We know that when we draw line segments from each corner of the quad, they form 4 internal 45-degree right triangles. It allows us to identify each component such as the length of segment BE, which is really what we call F. I won't do too much geometry. I'll always just give every segment a single letter, and we'll say that that's letter F. So you'll see how important that letter is. We know the length of side F in our 45-degree angle as the length of the hypotenuse. So that's easy to calculate. So it's simply the side of S divided by the square root of 2. It's pretty easy to get that far. Now that we know the side of S, and we now know the side of F, we only need to know the number of petals, which is we call N. And as each quad is rotated around the center of the disk, the value M is just simply 360 degrees, M, where we divide the number of petals, which gives us an angle of A. So essentially, the actual number of petals determines the angle of A. So those two are directly proportional as well. We also need to know half the angle. Later on, you'll see. We'll need to know half the angle of A, which is angle B. And here we need to determine one more particular angle, which is angle C. Thanks for hanging with me on all the math here, but we're almost done. Forming a new rectangle that we can solve for the radius r, because r is what we want to know. We know S because it's given. We start with S. We calculated F, just in review, and we need to know what r is. I also wanted to tell you, you can work the formula in reverse. I won't do that today, but if you happen to know the radius, you can back your way into the equation the other way around. So it does work in both directions. So based on that, we now have our equation based on these components that you see here, which again is r, the radius, is equal to S, the side of the quadrilateral, divided by square root of 2 times the tangent of C, angle C. Angle C is the hardest part to try to derive out of here to get it, but once you get this, it's actually pretty easy, but we're not quite done yet. You're probably wondering, how do I get to the next square? So as you remember, we talked about each petal gets smaller as it moves down in size. So we have to have some way to calculate that. And the way you do it is the second formula here, and we call the first S we have as given. The second S is S prime, and S prime prime, and so forth. So each one is a derivative of the one before it. And you need this formula, S prime equals the square root of 2 times S cosine of these angles divided by 2. So you keep feeding this into the equation over and over again, and eventually you will allow this each petal to get smaller. So for those of you who take computing and architecture or coding languages here, this is prime for a style of programming called recursive programming. I didn't use it in this particular case, but essentially in recursive programming, the program calls itself over and over again. And that's what you really need. It will keep doing it until infinity, until you tell it to stop. But as you can see at the bottom, you take the old S and put it into the new S, and you're back to the R again, and you're back in business. So let's look some at some of the qualities of all of this. What you're really seeing is that the one thing I've proven here again is that you have the spiraling effect. There's a reduction in disk floret petal size, that's happening. There's alternating positions, that's happening. So just like the flower, Walter Netsch had devised this in such a way that he's really studied the bio part of it, and he actually replicated it in this geometry. Okay, what's really important now is I'm going to discuss the 12-petal special case. The 12-petal special case is because that's what Walter taught us. He didn't get into all the other things. I figured out a way to do any petal that you could think of. But the 12-petal has all this harmony and synergy that's inside of it that makes it a remarkable tool to do many things. It's very modular. Last night we talked about modular architecture and how this is probably one of the reasons he used this system, because of its modularity. The one thing that's happening here is that what's distinctive is that the S prime, remember that formula I came for S prime? It's so easy to predict in this one. It's very simple. S prime is equal to F. It's kind of, if you think about a golden section has these kind of synergies that are happening too. So it's very similar in that respect. So let me give you an example of how that works in similarity. So in the 12-petal case only, you have S, but every other length of S has a square that has half the area, or S squared, half the area for every other square after that. And remember, we referred to every other as a very common equation called n equals 2k plus 1. That means every other one. Another version of the 12-petal case is the side, well, what happens to the side? So the side, also the area of a regular, oops, I think I might have gotten that. This one, I'm sorry, is the length of each side is half every other one, the length, not the area. The second one is the area is half every square. So every square is half the area. The previous one was every other square is half the length. So this is half the area for every other square. It's hard to imagine when you look at that first square and the second square is half the area. It doesn't look that way. It's very deceptive, but it's actually half the area. Now, I've been working with a few independent study students, and a lot of them want to work with me on this, and we're thinking about creating an installation design with projections from the ceiling. Key to this theory here, because what I discovered, you could actually take this notion of half the area, which is every square, and then map the tone of sound into that. So in this case, A, the note A, is 7,040 hertz, but then the one preceding, remember, is half the area, is half that, just like in music. So every one of those is half the frequency that tells us what that note is up the scale of the piano. So actually, if you gave each of these pedals, which is 12, and you gave each of them a note, so the A sharp, B, C, C sharp, then eventually you could actually create a piano based on this geometry. That's why I said there's a lot of synergies that are related to this. So this is where all the fun started. I knew that the 12-petal case was something that would function because that's what Walter taught us. But in reality, because I was able to put it in a computer program, any number will work. And particularly, prime numbers will work, odd numbers will work, any number will work. And I have a demonstration, an active live demonstration at the end. I'll show you how that happens. But 27 pedals, 17 pedals, 7 pedals, and 3 pedals. Wait a minute, 3 pedals? What is this geometry? So this is something I was actually looking for, something odd and new and strange. So when you use a number as small as 3, it actually folds in upon itself because the computer program is trying to resolve what I'm asking it to do. And so this was totally unpredictable. It creates a shape that we didn't think would happen. Part of my homage to Walter and discussion here, it's an emotional part, it really has to do with, if he were only here today, I could just show him all these different things that you know, he had potential because he didn't really have all the computers that we have to do this. So I apologize for the spreadsheet, but it's always good to look at the hard data as well, and sometimes a spreadsheet is best to do that. So what's going on here? All the blue ones represent where the angle A, B, and C, remember we talked about A, B, and C, are all integers or whole numbers. So they're even numbers. So in the 12 petal case, which is the orange one, the special case, A is angle is 30, angle B is 15, which is half of A, remember? And angle C is 75 degrees. But also in these other ones in blue, they're all integers. And all the other ones work as well. But as you know, when you have decimal points, you have to decide how many decimal points you're going to use before it stays accurate. But for the most part, if you use 10 decimal points, you're not going to have a problem probably at that point. There's a couple of weird things that happen. If you actually use a radius of 1, in the computer program, nothing appears on the screen. You get nothing. But if you notice, it's 1,154 quadrillion, etc. Negative, I should say negative quadrillion in terms of what R is. So it's easy to calculate it in numbers here, but what does that really mean? You can't really have a negative length. I mean, you can have a negative component on a XY coordinate, but what does that really mean? So this is actually pretty interesting. It tells us how computers could help us explore the unknown, really, if you think about it. When you take such a simple, and I did say simple geometry like this one, and then explore things like that. And so when I looked at doing -1, so what is -1 number? Number of petals is -1. Well, I know that's not possible, but what does it give me? Well, it's 384 quadrillion. That's the length of the radius. So if it was 100-inch side of S was 100 inches, it's 384 quadrillion inches, you know, what that turns out. So that was purely by accident, but it's really an interesting way to think about just the possibilities of the work you do. I would just have you think about all things are not visible to you, and you need to sometimes push the boundaries in order to explore what's out there. So eventually I had to take this, the equations that I had developed and integrate them into a computer language, which is processing for JavaScript. And so you can see in the red side all the equations I discussed. And then in black on the other side, you see the language that you have to translate that into so the computer language can read it. And so anyone who's done coding here knows that it only reads, you know, square root has a certain way of saying it. So you have to convert this. This actually took some time for me to do this, but it worked out okay. I'm going to show at the end actual algorithm working, so we'll get to that later, these two programs that I wrote. So I'll give you a live version of that. Now, the second program actually does the mesas. So it does the connections between the chrysanthemums to create field theory, or the actual mesa as he referred to it. And there's a formula actually you need to do that. So if you take, just imagine you take two flowers, and if you want to connect them, you have to take the second flower and move it somewhere to get it from point A to point B. And you do that with a coordinate system, X and Y, so that's why you see a comma down at the bottom. So actually, just to get the 2 points of the most edge of the two corners of two quadrilaterals to touch is actually the most complicated version of this. But if you did this calculation, they would actually touch if you did that. And then if you did something like make them touch in this way, then it's actually quite simple. You move, y is in 0, and you move 2 times the radius minus the length of S. We talked about how we arrived at F. And then this one, and each of these mesas have a name. This one's called M5. There's M0 through M6. I've been able to calculate M0 through M6. And I don't have them all here today, but M5 is really interesting. to do. And I believe that actually M6, this is the formula for M6. And in M6 is actually the most common one we used. This is the one Walter used a lot because there's a lot of richness in the overlap of lines. So there's a lot more opportunity to think about, you have both lightness and density and both kind of characteristics within that. And so this is the one he used quite a bit. Okay, we're done with math. Thank you. When I gave this talk at the University of Illinois last year, again, this presentation has evolved. We also talked about it at SIGGRAPH in 2021. One of the students asked me, he said, well, what are you going to do next? And I said, well, I want to look at it in 3 dimensions. So for the last year or so, I've been looking at that. So if you remember the mesa here in a computer graphic field here, we'll lay out the first mesa, and the technical term would be the ZX direction, which is flat on the ground, and Y is coming out of the paper, if you remember that. And then you take another one, you just rotate it vertically, if you can kind of see that. So now it's coming out of the paper in the Y direction, going straight up. So what you want to do is actually you create a cube that is based on the ground plane one first. So you lock it in. We've said that it's 100 by 100. You lock it into the ground plane. Then you take the second one and you lock it into the vertical plane. So now you have 2 of them. So there's an interaction between these 2. I like to call them they're almost like galaxies, and anyone who likes cosmology knows that 2 galaxies actually collide and they create something new. So actually we can put them together and they look like this. And then for most of you who are using things like Maya or 3D Studio or Rhino or SketchUp or anything you can think of, you can start using the Boolean tool to start thinking about creating space and creating voids. In this case, I looked at the bottom piece, subtracted from the top piece, or I used the command we sometimes refer to in Boolean as split in order to eliminate one piece that overlaps both of them and creating a void between 2 spaces. I know that Boolean is nothing new, but I do want to say that Boolean operations in 3 dimensions is one of the most powerful tools ever created for modeling. I mean, there were many others like surface of revolution and blob architecture, how you can do that. But Boolean was really one of the most powerful, I feel, that I've used also over the years. So I end up with this form where there's a collision between these 2. And it ends up being, you don't stop there, because you realize that there's variations on that. There's different ways of interpreting what's transparent and what's not transparent, what's dense, what's not dense. And actually I came up with really quickly about 6 or 7 of these variations, and realized that I could start doing some things with that. This is, we'll just call this a site sculpture. It's not necessarily a building. It's a site sculpture, and oddly enough, I realized that I needed an armature for this all to connect to. And that armature is just a simple grid of 100 by 100. Remember, the S is 100. It's 100 by 100 by 200 high, and et cetera. And I could lock those pieces into there anywhere I wanted to take it. Those pieces that I'm talking about here don't have a name yet, but for those of you, again, who indulge in math, when you're not doing architecture, you have nothing else to do. There's such a thing as called a tesseract, which is a 4-dimensional, the shadow of a 4-dimensional hypercube. We're going to call this a Nesseract, so it's a Netsch rack, so we'll call that. So I actually locked in the Nesseract, and then I rotated, flipped, and did other things with it in order to lock it into this grid system. And then I could start exploring gaps and spaces and shade and shadow, moving from compression to expansion and looking at different ways how this form could work together. And then eventually starting to study the sections. This is actually a section of that form and looking at the sections for it as well, here and here. And then ultimately, I started to look at, you have to bring out V-Ray and see what V-Ray will do to it. Because using a tool like V-Ray helps you figure out like what the reflections are. When you're reflecting off a glass, it starts to change the environment significantly. And so you really have to go into this mode in order to understand what's going on. Someone asked me, was this a self-portrait? Maybe. Maybe. Okay. This is the chapter I had to add 3 days ago, which is artificial intelligence. So for the students here, you probably had conversations with their professors. I know at our university it's a big deal, but it's only been a big deal for about 9 weeks because even 10 weeks ago it wasn't even on anyone's radar. But there's a program that I use extensively. Everyone has heard of ChatGPT, but there's one I use extensively called Midjourney, and I'm sure some students have used that too. Midjourney, by the way, is hard to create architecture in Midjourney, but it's easy to make a Midjourney, in Midjourney, an architectural model of an image of a building, but it's so far yet to be seen if we could actually create architecture using Midjourney. And I've actually got into some conversation with people who want to talk about this, and they recognize that there's some limitations to AI, and that's just for now. For now. The summer, who knows? Next year's, who knows? So maybe next year they'll figure out how to do this. So I asked the computer if you're familiar with how to use, this is called the three basics versions of AI chatbots are text-to-text, which is ChatGPT, text-to-image, which is Midjourney, and soon this summer, text-to-music, which Google's working on. And I've actually tried the beta on that, and you just type in jazz song and 4/4 and the style of Miles Davis, and it actually writes a whole song for you. So this is actually text-to-image. So I asked in the prompt here to create an abstract chrysanthemum with 12 petals, symmetry. I use the word symmetry is really important to use in a prompt if you really mean symmetry. And I just happened to use the word yellow, and I thought, well, this is not really what I'm looking for. It still looks like a flower. And then I changed a couple things. I said, do it in line art. These tools that AI don't quite understand, like they don't understand what the architect's thinking yet, really. When I say line art, I mean like a drawing, you know. So really, I shouldn't say it can't be done. I just said I have figured out the words to use to say it, to get it to do that. And that's what I love about using this tool, is that you've got to really dig down deep inside to figure out how to say things in words and convert it into something that's meaningful in an image. It's really, in my mind, kind of a difficult thing, but somewhat enjoyable to do it. So I actually, in this one, told it to not draw a chrysanthemum on the left here, but to draw quadrilaterals. So you see how I just changed the word a little bit? And by doing that, it starts to develop something different. This also relates to when we talk to our students about, and other professors I've talked to, I've been talking to a few other professors around the country about this, how students are actually fooling around with this tool, and they're saying things like, develop me a building, a 12-story building in the style of Architect X. I won't say a name, Architect X. So actually, Midjourney is actually really good at that. It'll actually go into the internet and scour every image of that architect, and it creates some kind of amalgam, and you actually get a building that looks like the architect had actually done it, but it doesn't really exist. But it looks like a building this person did. So we actually are trying to encourage students not to do it that way. Try to find the words that mean what you're trying to do, rather than just find an architect's name and use that to do what you want to do. So I used over here spiraling squares. I used the word squares for that one. And I said, well, it's getting close. It's not bad. And then on the one on the left, 12 spiraling quadrilaterals revolve around the center point at right angles. So I used that as a prompt. Geometric, symmetry, and line art. And I thought, no, not quite. It's getting better. And then the last one on the right is just where I had to stop. Otherwise, I would still be working on it right now. Because one of the difficult things, one of the exciting things about working in Midjourney is that as a graphics and visual person that I have been all my entire life since age 5, this is like the tool I've been waiting for my whole life. I mean, this is like really amazing. So sometimes I unfortunately have to say I've spent a few hours on the weekend doing this, and I've run out of gas. And we call gas. You have to feed things on the computer cloud with what we call gasoline, and I've run out of gas a few times doing this. So that's a sign, actually, you've been on it too long, actually, by the way. All right, so that's my presentation, really. I have a couple of demos to show you. So this is actually the first one is actually the demo for the chrysanthemum itself. So as you can see, I can change with a slider, I can change the actual S. This is actually changing S by making the side of it bigger. I'm sorry, this is actually number of petals. The first one is N. This is N. This is S. So the side of S, and you can see what happens when you do that, so I can keep. And then this last one is how deep, how many layers in circle that it goes into. So for this one, you have to readjust your center just like on a map, on Google Map. So I can go into depth, how deep, and this one is limited to how far I can go, but you can tell how deep. I just want one layer, I could have 2 layers. This is actually 3 layers, and I can keep going. So this is that program I wrote is actually doing this in real time. And for those of you who haven't used p5.js, it's actually, I was actually trained in a program called ActionScript, which is Flash, and Flash has been totally deprecated now. p5.js is a great substitute for Flash. It can do everything that Flash can do in a much more safer environment. So I would highly recommend, and it's very easy to learn. It's very easy to learn. So this is the Mesa generator, and you can see I have M1, the connection where the 2 points are meeting in the center here, and I can just, in this one, just look at different ways of connecting the length of that. And then also the transparency if I wanted to fool around with that. But here's actually the M2. So each one is actually more denser than the one before it. And then M3, and then M4, and then I've also recently figured out M5 and M6 as well, because again, I had to use that formula, that XY component formula, to tell the computer to do this, and eventually it would get there. So in conclusion, I would just probably say that why talk about grid systems really at all? I teach second year design studio, so what happens is some of the students I have never drawn a building. This is the first time they've ever drawn a building. And a lot of them actually create a grid system on their own. And some of them asked to help them with a grid system because it's part of your concept. It's an organizing principle. It's how you organize your work, and you can use a grid system in order to do that. And Walter Netsch's version of that was just unbelievable in terms of when we got to class. I think we just, the first couple of days, we thought we didn't know what we were literally in for. And then finally, I wanted to say that one of the students asked me this. I'll ask this question before somebody else asks me. Was that have I ever had a chance to use this in an architectural project? So I've never owned my own firm, so that that has something to do with it. But I did work at a firm It's actually like 6 blocks from here. I won't say who it is. And we had a design project, and they decided to do it as a competition in the office. This still happens sometimes. It is not that often. And Damon, you go work on this one by yourself, and Joe, and so forth. And so for a couple of days, we got to work on this. It's a cemetery project. And so there's a lot of organizing aspects to that. You know, there's the mausoleum, there's all the grave sites, there's the regions, there's always a lot of cemetery has regions in it, and nodes and connections, so it has all those pieces to it. And so I came back a couple of days later and everybody posted up on the wall, and I actually got to go first. And what did I do? Field theory. I laid it all up on the wall, had everything, all this, you know. And so I turned around and I looked, I turned around and no one would say anything because they had never seen anything like that before. And it was like, it was speechless. And actually my boss at the time, he actually did tell me he really liked it, but we didn't use it. We didn't use that one. It's really complicated. It actually is not as complicated as you look. You can make a rectilinear grid. It could be really complicated. This is just something new and different. So I was maybe a little ahead of my time there, but I have tried to use it. Okay, so that's my formal presentation. I just want to thank you so much for your attention, and I'd be happy to answer any questions for you.
Questions from the audience?
Damon, I think you answered the question with your own question before I got to ask the question, but you started off talking about the design of the chrysanthemum, and I assume it applies that efficiency and surface area for growth and sustainability applies to many of these geometric natural objects. So when you're working in your land sculpture, I think you called it, and when you started to do sections like we're seeing now on the screen, do you think about efficiencies and surfaces? And then the next question kind of is similar. When working with the AI, could you put the word LEED certified or silver into that, and what might come up?
In regards to the second question, the students in the room, how many of you have tried AI? ChatGPT first. How about Midjourney? Oh, a lot of you have already done it. So you know the question he's asking. You can answer the first question, the second question first. AI in terms of text to image is just a 2-year-old. What I've been talking, you have to keep one thing in mind about AI that's currently in this version, is that it requires human beings to train it. And I've read recently that there's a group in Africa, a group of people who have been doing, they're finding these people all over the world who have the manpower, enough people, and the time and knowledge to actually go in and train the models. So the answer to your question is they haven't gotten there yet. That's why I say that's just today. So I have to check on OpenAI or AI things we're talking about today. I have to update to my class every week because it's something obsolete from last week. You know, something new happened dramatically, and as I mentioned to some people the other day about how someone asked ChatGPT to write an episode of MASH, and it did. And according to the actors, it's not bad. You know, so, but it's easier to train, I think, in the literary world, in my opinion, it's easier to train in the system to do that. What it really is telling you all here, really, especially the young architects here, you all have to get involved in that, this training thing. in order to help bring this tool to a level where it becomes an architectural tool. In reality, we can really do some of the things with the words you could come up with. But right now, my guess is that most of the people who are doing that are not artists necessarily, or architects, I should say. They're probably not architects. But it's coming. Now, the first part of your question again was, oh.
Do with the geometry of it.
Yeah, so one of the things I was thinking about is that the light. So now that I have all these optional Nesseracks, I can actually start thinking about optimizing the rotation of each one based on its location in a real site. So the sun angle and shadows can be manipulated, and eventually you would start to see a pattern of how they're actually working that way. So that's as far as I've gotten on that one. I'm interested in spatial relationships, as I said, compression to expansion and things like that. Movement between one space to another, where their quality of openness changes. So that's what I'm looking at in that one so far. Thank you.
Any other questions?
David, I got a quick one.
Go. Hold on. Right
Does
after
it
this
work?
one.
It's going, it's broadcast.
Go ahead.
Can you hear me?
Yeah.
Yeah, so the Air Force Academy, it's the whole campus that's laid out in the field, the field concept. So, you know, it'd be kind of interesting to see a few of those kinds of projects that are, you know, Netsch's work. I worked on a project in Ann Arbor well, it turned out to be Pfizer in the end, but it started out as Park Davis, and then it was Warner Lambert. But basically, the lab building and the administration building were done by Netsch, and he used basically a multiple of 7 in terms. So the base spacing was 21, floor to floor was 14, et cetera. So it was kind of obsessive. It wasn't quite the way that you would have this sort of computer-driven thing, but there was a way in which he established the field in all directions. So, but I mean, I think you could look at some of his other work and see how the field theory came into play. Also, he got his license taken away because he didn't have his continuing education credits after he had retired from SOM. Anyway.
Yes, as I mentioned, there's I know of about 20 projects for sure. There's more than that, actually.
He asked. It's the same issue.
He was really, some of them are more obvious than others. Some of them, one of the more interesting one is his contribution to the Chicago Architecture Fair Tower competition. And he actually ventured into 3D in that one. That's the only one that I've ever seen. All his buildings, of course, are 3D. But I do want to clarify one thing, especially for the students here, is that as far as AI or what I've just shown you today, this is just a tool. It is not the architecture itself. And just as CAD was not the architecture, or now BIM is not the, it still requires human beings to.
Pencil and paper tools as well.
paper tools too. So paper is a tool. We went from, I have another lecture on that. I started my career in graphite, then plastic lead, then layer system, then CAD, all in my one lifetime, then BIM, then 3D, which started with Form Z, which I started with, if anybody remembers that program. And now we're into, there are actually some programs that will actually lay out an entire building. I didn't even talk about that, where it'll lay out a condominium tower with all the rooms and correct corridors and all that are already there. So we need to merge AI with that tool in order to make it work. So, Gary?
Damon, what Bill said, I was going to ask, examples of how Walter applied it to, sort of the imperatives of a space program, the functions, how do you reconcile it with this geometric system? That's, I was just looking for examples.
Yeah, my best response to that is don't be fooled by all this jazz. when you look at the floor plans of his work, and I know Carrie, what an amazing programmer and planner you are. It would meet your standards in some way. I want to say that it's real architecture. And even the short time we spent is like only 3 months. And he just didn't have all that time to, I was asking him questions like that too. And he just didn't have the time to answer all those questions for me. But when you just look at his plans or go to one of his buildings, they work. It's just not for fun here. They actually, he was a serious architect, and he actually made that stuff work, yeah.
You might highlight the sort of, like a dialectic between these different systems and how they conflict and how they sort of conform too, you know what I mean? As far as, the geometry suggests a certain way and maybe the functions contrast with that, and so there's a tension between them. You might be able to exploit things like that. Just looking for different ways of how you can make these systems interact and stuff.
This being in a class like with someone, I didn't know how important a person he was when I took the class, but and obviously you could see how it affected my entire career in some ways. But he really didn't there's a lot that he left out in those conversations. But I think he did one building was a laboratory, and you all know how complicated that can be as a planning exercise, but it totally works as well. You would think all those angles, but I would also say this, Carrie, is that I've seen people design with a rectilinear grid and it didn't work.
Right.
It just goes to show the tool is just the tool.
Yeah, I wouldn't even challenge that it wouldn't work. I would just love to see how it worked.
Yeah.
That's what I'm saying,
Yeah. I would say go to University of Chicago, and I would, I've actually never personally been in one of those buildings, and you and I will both go there, and we'll go check it out.
Damon, we have a question from online.
Okay.
From Francisco Landeros. Damon, thank you for the great presentation. I think I heard that you have participated in NAB. I would like to know how we can push these studies to be integrated into architecture programs. And he also said he's interested in learning more about your programming journey in architecture. Do you have any way I may reach out to you?
Yeah, I'll answer the second question in a minute. So I'm no longer on the board of NAB, so I'm free to offer my opinion. It's just my opinion. I think, first of all, the NAB structure, I know you all are going through this right now, but generally the 2020 conditions are actually, most people find them much better than the previous versions in the past, because it gives you more flexibility to demonstrate how performance really than as opposed to exact criteria for certain things. You can demonstrate how you do things rather than say they have to be done exactly this way. So I think that most people find that. But having said that, what's really important is that we keep up with emerging technology. So in my view, because I used to teach computer architecture and things like that, so in my view, every student, how many students in here have taken a coding class? Architecture students, raise your hand. 1. That's my answer. It should be all of them. Because every business is a technology business, including architecture. We can either have people who are venture capitalists who are making money off of things they sell us, or we can do it, okay? And they need us to help make these tools better. You can see it already in Midjourney. It's just not there. It needs our input to help make things like that better. The second question was?
He just wants to know how he can reach out to you to get more information.
We'll send him my number.
Okay, I'll get his email.
I have another lecture where I talk about me more, talk about my journey. People ask me that question. As you all know, I'm a graduate from here. Without making a long conversation, I'll just say, I love my school. And you will too when you get down the road. I feel grateful to be a graduate from here. You maybe don't see a lot of people my age say stuff like that about this university, but I'm really, my trip here, I've been here for a week and I've been treated to just the nicest people I've ever met. New people in different administrative positions in the School of Architecture and my friends here I used to work with. So it's been a wonderful week in that respect. Okay.
Any final questions?
Welcome home.
Yeah.
I have one. I need
We need to use the microphone for the YouTubers.
Okay.
No, I second Damon's comment about LTU and what they give you in the search. I'm still searching, by the way, but and I've been doing it for many years. But one thing, Damon, I guess because I met Walter Netsch at SOM in '79, and the thing that we all do as architects is that we search for beautiful geometries, and be it chrysanthemum or some kind of numbering, we have to find a structural grid or some kind of structure. We have to look at window geometries and get natural light in. And we want it to be beautiful. We want it to be logical. We want to find logic in what we do. And it doesn't have to be dense. It can be pulled apart and abstract. And I just wondered if you've explored the field theory in other ways that maybe could be applied directly and maybe aren't symmetrical and have different kinds of geometries from that.
Yeah, it's a really good question, Alan. Thank you. Probably the hardest to answer. You came away from that class actually saying there's a key. You put the key in, you will unlock the secret. Well, that key, I've been working on the key for 40 years, it's still going on. And I've come to realize there is no answer, but I do have a sense that there's something there that is richer. And I started by doing it kind of based on Steve's question, really as saying there's things where it can relate to the environment that I don't think Walter had gotten into in much depth, that I can see now because I've looked at variations of this Netsch and then look at the variations, I see that I can actually implement those in terms of real life site design issues, programming issues that we really have to work with. I would say that some of the buildings that Walter Netsch did were actually extrusions of these. As I said, if he were here today, we could have a great cup of coffee talking about what you just said, But I have to be careful. I don't actually try to put too much pressure on myself to say, I'm going to have this is the answer to the question. It's the journey actually is what I'm really enjoying. And I might discover some new things. What's important, I think, is every year I need to discover something new, or every month if I can possibly do it. Great question, Alan, thanks.
Anyone else?
Any students got a question? This is your last chance. Okay.
I'm not a student, but...
Okay.
Wait, hold on, please. Getting a workout.
Is there any similarity between what Walter did and Frank Lloyd Wright and how he broke down the grid system, essentially, and knowing how to also, since a lot of it was geometric, of course, you're able to feel a certain way when you go into his house, like it's more human or whatever. Is there any parallel to what Walter did in that regard, or what you're working on right now?
Yeah, good question. I'm staying in the Affleck house, so I'm getting another dose of this. I've been to a lot of Frank Lloyd Wright houses and projects, and I spend an hour or two in these things looking at things that other people don't look at. And Frank Lloyd Wright definitely had his own grid system. It's so much different than what we're talking about here. Another good example, I would say is a better example, is Lou Kahn. So when you look at the bathhouse in New Jersey, there's this grid system that's going on there. And I actually tell my students about that project, really. And then you can compare the two, and the only thing you can really say is just two people in a different universe mindset thinking about two different things. But however, so this question came up the other night. It's about proportions. Because any grid system has to be based on proportions. And it just can't be random. And I've talked about the proportions, about half the length and then half the area, and how this halving was going on. But you can see in Lou Kahn, you could see this proportional relationship between. So the important thing for students to recognize that a grid system is nothing without the analysis of its proportions, because then you end up with basically a random structure in the end. I hope that answers your question. Okay, thank you.
Okay, I think we have one more.
Excuse me. Okay, thank you for the wealth of knowledge. This is a question and a statement about the young architects.
Sure.
I'm interested that there are no questions and they have all this knowledge here. So give me a glimpse of what are the students like that you are teaching. And I understand we all want to be different and do things different, but there are principles that allow you to do that.
So I'm actually part of a working group at UA on connectivism, which is, it's a great question because it's two parts of this. One, direct to the students, one, you're addressing what you're saying, is that teachers have to change. So it's easy for me, the first class I ever taught, everybody was on their phone. Now, don't everybody react to that, I said that, okay. But I used to think it was their fault, but it's my fault. So I have to change the way I teach because the world has changed. Technology has changed. We have to be more interactive. I try to workshop everything now. I don't ask open-ended questions. Things like that my teachers say, hey, so what do you guys think of this? And we would sit there and say, well, I'm always the one that raised my hand all the time. I did that a lot. But everybody doesn't feel comfortable. But I've talked to students about, let me stop here and just say this one thing about the students. You guys are amazing, because you have a technology and the future right now that's facing you guys is incredible. And you have social media clouds, artificial intelligence. The capabilities you have to transform architecture is enormous. And I love sitting down with students, just chatting with them about stuff like that, because they just have an amazing future in that respect. So part of the answer really is just changing, I think as a teacher, just changing the way I do things in order to address you remember they say that a person forms their self by the time they're 18 years old. So you are who you are when you were when theory. So you got to recognize that whenever you have a cohort, you got to know what that is, because you can try to force the old school thing on them and then, it doesn't work. So I enjoy just actually evolving. I've taught one class 7 times and I've tried the best I can to teach it the same way every time because isn't it easier to do that? But I can't, because it's a computing class and I have to keep changing all the time. And I like that. It keeps me, excited every day when I go to class. Did I get most of your question there?
No.
Okay.
No, what you said is phenomenal.
Mm-hmm.
But also that transcends with organizations.
Mm-hmm.
That you have to teach differently, you have to attract differently.
Mm-hmm.
And we all have to be ready to move and just pivot.
Mm-hmm.
What you're saying, bringing things in from the 40 and taking it to now the future. Mm. So I even wonder, how are these students inspired? Where do they get inspiration from to be creative?
Mm-hmm. Well, I've talked a little bit about, I didn't talk enough about how this inspired me. So just look and see how long it's been going on. Without making too long a conversation about that, the thing is that it's a great question, so there's something else to share with the students here. You've got to look at everything, I spent a lot of time at DIA when I was here. I've seen Van Gogh, I've seen Diego Rivera, I've seen Wyatt. I mean, every time I've gone to those things, none of the people I just mentioned are architects, see. It's all about art and design is intertwined into what we do. And I would encourage you all to go see every possible aspect of design and art that you can, because they will find its way back into what you're doing as an artist. You will learn something in every instance of that, and you'll come back energized with new ideas. Even Mid-Journey does that to some degree. I create an image. I'm not trying to copy the image. I'm not trying to say it's mine. It's not mine, it's the computer's. But the reality is it certainly inspired me to do the answer that I was looking for. So that's the unique thing that this group can do that no one could do before that. So I think I'm going to enroll again. I mean, you know, can I, you know, because this is going to be fun. This is really going to be fun.
All right, I think we're going to have to stop now, unfortunately. And before we thank Damon, I do want to say that, as he mentioned, he's staying in the Affleck House, and we're having a dinner tonight at 5 p.m. for students and friends of the program. And if anybody is interested in attending that dinner with us, please see us down here in a minute or so. Otherwise, thank you, Damon, and this has been great.
Okay, so you unlocked something for me. So, you know, City of Detroit, turns out 15,000 plus, 30 by 100 lots in the Detroit Land Bank. And the thing is, when we inherit that grid system that is that was defined for a totally different
As well
purpose,
as circus,
then
you
we
know.
build boring things on it, don't we? Because we start with that rectangle and we're like, we're stuck with a rectangle. And I'm falling into the trap and we're 3D printing houses in the city. So what you showed me was that, like, okay, fine, you know what? We can use that principle within a bounding box that's a rectangle and then maybe repeat it this way. Okay, you can't go too far with it.